Let's take a look at another example. Again, we want to try solving the linear system AX equals B, where matrix A is this matrix here, vector B is this vector here. Okay, and we want to solve for vector X. As we've seen, this is equivalent to solving a linear system of equations. To do that, we want to produce the augmented matrix with our coefficient matrix A, and in the augmented part, vector B. So for this problem, that's going to be 3, 1, negative 3, 0, 0, 3, 3, 1, 0. That's matrix A, our coefficient matrix. And in the augmented part, vector B, 17, negative 6, 11. Okay? Now again, we could solve this by hand. It's actually not difficult, this one. But we're going to let the computer do it again so we don't have to think too hard. So I'll let M again be my augmented matrix, since I don't want to call it A because I already have a matrix called A, right? So when I augment it, I don't want to call this A also. So I'm going to call it M. This is my augmented matrix. So just row by row, 3, 1, negative 3, 17, 0, 0, 3, negative 6, and last row, 3, 1, 0, 11. I want to find the reduced row echelon form of matrix M. I want to print it so it's pretty, easy to look at, easy to read. Okay, and I have my answer. So I have 1, 1/3, 0, 11/3. Second row, 0, 0, 1, negative 2. And last row, 0, 0, 0, 0. Okay. Now notice I do have a solution. There are no rows here that would tell me that if that say that I don't have a solution. Again, such a row would be all zeros on the side with the coefficient matrix and then something non-zero on the side where I don't have a coefficient matrix. Okay? If I have that, then I have no solution. This row just means 0 equals 0. That's true, not especially helpful, but it is true. Okay? But what I do notice is that I have 2 rows with non-zero entries now that I'm in reduced row echelon form. 2 leading entries. That means the rank of the matrix is 2, yet I have 3 columns. So I'm going to have a free variable. Okay? This column doesn't have a leading entry. So that column, the variable corresponding to that column, is going to be the easiest choice for my free variable. All right? So let's start putting these equations together, interpreting our results here. So again, I'm going to think about this as x, y, and z. I could think about it, by the way, as x1, x2, x3. The original problem doesn't say what vector x is exactly, so I could choose what to call my variables. Okay? I'll just call them x, y, and z. No need to be fancy here. Okay? So this last equation, not especially helpful. It's just 0 equals 0. I'm not even going to bother writing it down. Okay? This equation tells me what z is. Z is equal to negative 2. Okay? The first row, if I write down the equation, it will involve 2 variables. And that's why I need a free variable. I have only one equation here, but it's relating 2 variables. So since x already has coefficient 1, it's easiest to choose the non-leading variable to be the free variable. That's General rule of thumb, it will always be easiest. So the column without a leading term in it, leading entry, that's the column that you make your free variable. So I'm going to choose y equal to some free variable, which I will call t. Okay, so if I plug that in here, I get x plus 1/3 t equals 11/3. Solve for x. X is equal to 11/3 minus 1/3 t. Okay? And so my solution, vector x, my vector xyz, if I kind of put all my pieces together, component x, that's 11/3 minus 1/3 t. For y, y is equal to t. And for z, z is equal to -2. Okay? And what I'm going to do is I'm just going to break this into pieces. I'm going to break it into a vector without t and break a vector into only the components, only the terms in each component with t. So let's do without t first. So for the first component, the term without t is 11/3. Second component, I don't have a term without t, so 0. Last component, -2. And now, for this vector, I'm only going to have the terms with t in it. So the first component, -1/3 t. And since every component here, every term here will have a t in it, I'm going to put the t on the outside, so I only have to write once. So -1/3 t. Second component, just 1t. 1t. And the last component, there are no t's, right? So 0 t's. 0 t's. Okay? So this is our solution. Any point, any x, y, z that can be expressed in this form would be a solution to this system of equations. So if I set t equal to 0 and set x and y and z equal to 11/3 and 0, -2, that would solve the system of equations. Okay? If I set t equal to 1 and get 11/3 plus 1 times -1/3 for x, and 0 times 1 plus 1 for y, and -2 plus 1 times 0 for z, that would be a different point that solves a system of linear equations. We have infinitely many points that solve this system. In fact, we recognize the form of this equation. This is the equation of a line. It's the vector equation of a line. So we have all the points along this line that can solve the system of equations. Now, you may recall that when we have the vector equation of a line, that vector equation isn't unique. All we need is a point on the line and a direction vector. Okay? Would describe all the points on the line. But there are lots of points on the line to choose from. I just have one here. There are lots of direction vectors to choose from. I could scale this direction vector. It'd still be pointing along the line in the direction, right? I'd just be changing the length. So this is one possible way to express the solution. But any other way of writing out the equation of the line would also work. For example, I could choose let's see, let me make sure I get this right. For -1, -2, that is a point on the line. If you choose t equals to -1, 11/3 minus -1/3 is 12/3 or 4. 0 minus 1 is -1. And -2 minus 0 is -2. Okay, so this is the point on the line that I get when t is equal to -1. And I could choose any direction vector also. So for example, if I multiply my direction vector by 3, I get -1, 3, 0. It's pointing in the same direction. All I've done is I've scaled it. I've just changed its length. But this is just a direction vector. The direction's the most important part. So this is an equation for the same line, but represented differently. Because it's an equation for the same line, it's a different way to express the set of solutions to this system of linear equations. Either one of these will work. Either one of these is a solution to the system of linear equations because they describe the same set of points. Okay? They describe the same line in three-dimensional space.